Okay, so now we're looking at second degree linear homogeneous recurrence relations. So here's our linear second degree because there's two terms. Homogeneous, we have no function of n added to the end. And to solve this, we're going to go with a similar way as we did with our last example of first degree linear homogeneous, and we're going to use an auxiliary equation to help us. So notice we've got three terms here, and I can think of this like a quadratic. And in fact, the quadratic is going to be our auxiliary equation. So the first thing we want to do is we want to rearrange our formula to be equal to 0. Oops. And then the auxiliary equation is going to be x squared minus ax minus b equals 0. So we're going to solve this and get our roots. So our roots are going to end up being alpha 1 and alpha 2. And depending on the nature of those roots will depend on our general solution. So the general solution, general, has the form u sub n is equal to a times alpha 1 to the n plus b times alpha 2 to the n. But depending on the nature of our roots, this is going to change. So in the case that our discriminant is greater than 0, so I'm talking the discriminant here of the quadratic, so that would mean we have two real distinct roots. In that case, this is going to be our general formula, and it doesn't simplify anymore. Alpha 2 to the n power. In the case that the discriminant is equal to 0, so we have one repeated root, what this ends up simplifying to is going to be u sub n is equal to a times alpha 1 to the n power plus bn alpha 1 to the n power. In the case where the discriminant is negative, so we have imaginary roots, we can end up writing our solution either in imaginary form or in cis form. And hopefully you remember that from your higher level class. We're going to look back at it, but you can see what that'll look like. So we're going to end up with un being equal to r cis, that would be our root, would be r cis plus or minus theta. So our un is going to end up being r to the n, a cos n theta, plus b sine n theta. And this comes from u sub n being equal to a times alpha plus beta I to the n plus b times alpha minus beta I to the n. Beta I, alpha minus beta I to the n. So this would consolidate down in r cis form to be this one. So r to the n a cos n theta plus b sine n theta. All right. We determine, regardless of our cases, we determine then a and b using our initial information. So always, we're going to end up knowing what our U1 and U2 are, or U0, U1. So we'll use those to solve, and we're going to look at some examples of each of these cases coming up.